Okay, so I'm going to try and repair a little bit the last lecture, which I was frankly not happy with. I gave a proof of the rank nullity theorem. So I'm going to do that proof again, somewhat slowly. And again, as usual, you are supposed to stop me and whenever you find something is not clear, and I strongly encourage you to do that. I really appreciate if you stop me whenever I am unclear. Even if you are a bit shy, please do this. Okay. So let us start. So remember, so just to go back a little, we are in the final part of the abstract introduction to vector spaces, and we have defined dimension, and we'll mostly be dealing with finite dimensional vector spaces, except possibly in some exercises. Okay, so basically the idea is that if you have V is a vector space, we have two notions: the notion of a linearly independent set and we have the notion of a generating set. And then if V is generated by a finite set of vectors, the basic result is then if S generates V, and so let me call S2 generates V and S1 is linearly independent, number of elements of S1 is less than or equal to number of elements of S2. So this is the basic theorem that I have indicated a proof using a result from matrices. So you are supposed to know how to prove this theorem. Okay, use the following result. Use any linear map from Rn2 to Rn1 with N2 bigger than or equal to N1 has a non-trivial kernel. If there are more unknowns than the number of equations, you can always find a non-trivial solution. So from this, it follows whatever I have drawn in red follows. So you should know how to prove this, how to use. I assume this fact. Assume the fact in blue to prove the fact in red. So this arrow, you should know how to fill in this arrow with arguments. Then I stated a multi-part theorem, of which one of the important parts is the rank nullity result. Which said that if if V1 is finite dimensional, and my notation might be different from the notes. Let me try and keep to the notation so that you are not confused. If V is finite dimensional and V T V to V hat is a linear map, then dimension of V is dimension of kernel of T plus dimension of image of T. So let me go through the proof because I'm not satisfied with the way I talked about the proof in the last lecture. Okay, so will equality be there in the blue box N2 equal to N1? Thank you. Shubham, thank you. Thank you for catching that. It's absolutely, yeah, this is a very, very silly thing. It's, in fact, you need a strict inequality. Thank you so much for catching this. Yeah, this must be strict. If it's equality, you can't conclude this. Yeah, I really appreciate this. That would have been a disastrous mistake. Yeah, thank you. Very good. Yeah, so let us. So now I'm going to go through the proof slowly, and hopefully this time clearly. So, and please, everybody, pay attention. And the moment something is not clear, just unmute yourself and tell me, because I am not looking at my computer screen often, so I may not see a chat or I may not see a hand raise. Yeah. So first of all, first point, image of T, which is a subspace of V hat, is finitely generated. That is because if I take any set of vectors whose span is V, the first vector space, and if you take the images of all these vectors, so you get a subset in V hat, that will generate the image of T. So this is the first thing that I'm not going to spend time writing out, but if any one of you has confusion about this point, you should tell me, and then I am willing to spend time on this. See, the point is, the way I have stated the theorem, I have assumed that the first vector space V is finite dimensional, but I have not assumed anything about V hat, because all the action is taking only in the image. The image is a subspace, and I don't care what the bigger V hat is. The image is going to be finitely generated, and therefore it's going to be finite dimensional. So what, the bigger vector space V hat could be possibly not finite dimensional. That will not affect us, because V, as far as V is concerned, and as far as the map T is concerned, only the image is relevant, and that the image is finite is generated by. So take any set of vectors that generates the vector the space V. So supposing V is n dimensional, so I have n vectors that generate V. Then T of V1, so call them V1 to Vn. Then T of V1, T of V2, these are vectors in the image, because by definition of the image, and any vector in the image is a linear combination of these guys. Because any vector in V is a linear combination of these, of V1 to Vn. Therefore, any vector in the image is a linear combination of TV1 to TVN. Is this point clear to everyone? I'm saying this in words because you can think this in words. You don't need to write the mathematics to grasp this. You should be able to think this argument just in words. If anybody has confusion about this, please unmute yourself and tell me, and I will write out the argument. So let me at least write out the statement so that you can all be sure what I'm saying. So that is for if U1 to UN is a basis for V, TU1, TUN generates image T, even though the set TU1, TUN need not be linearly independent. I'm not claiming that the image is linearly independent, but it will generate the image. Yeah. Let me be consistent about my notation. I'm not, yeah, I just mean the set. Okay, so I'm assuming that I can go on. Okay, so
sir,
note that, yeah.
That if U1, U2, UN are is a basis of V, then TU1, TUN should be linearly independent now.
No, they need not be. They need not be.
Like if U1, U2, UN is a basis, then TU1, TN should be UN should be the basis for the image.
No, they need not be a basis for the image. That is my point. But they will span the image, but they need not be linearly independent. So, for example, I'll give you an example. So example need not be. Example. V is R2, V hat is R, T of XY is X plus Y. Okay, this is a linear map from R2 to R. And what is the image of T? Shakti.
Yes, sir.
What is the image of T?
R itself.
R itself. Very good. Yeah. Okay. Okay. But what is the dimension? Okay. So now I'll give you two arguments and so basis of R, basis of R2. So take U1 to be 1, 0. U2 to be 0, 1. What is TU1?
1.
1. What is TU2?
1.
1. So TU1 is equal to TU2.
Yes.
So they are not linearly independent. Right? If I have two, if I take a vector, so this is a so of course here it is just, TU1 and TU2 are equal, so we can say that the set is linearly independent. So this is a bad example. So let me give you another example. T is equal to X plus 2Y. Yeah. So I'm changing my example because this was a bad example. X plus 2y. Okay. Now what is TU2?
2.
2. Okay. So if I look at the set TU1, TU2, this consists of two elements of R2, namely it consists of 1 and 2. But are they linearly independent?
No, sir.
No. So here is a counterexample. So, but TU1 and TU2 together generate R, but they are not linearly independent in R.
Yes.
Is this clear?
Thank you.
Yeah, thank you. Okay, so now, second step, I have to now show that dimension of V, which I take to, so let dimension of V equal to n. This is just defines n, the integer n, and let dimension of kernel T equal to, let me stick with my notation. L. So, so L is less than or equal to n, right? Because kernel T is a subspace of V, so it has a dimension which is at most the dimension of V. So this we know. We know this. Okay. So choose the basis V1 to VL of kernel of T. So this is a linearly independent subset of V because it's a basis of a subspace. So it's linearly independent as a subset of V. Is that clear to everyone? So what am I doing? I have a vector space V. I have a subspace, the kernel of T. I choose a basis of that subspace. The subspace has dimension L, so the basis will have L elements. So I choose a basis. And because it's a basis of the subspace, this is a linearly independent set of vectors in the subspace. Therefore, it is a linearly independent set of vectors in V. So this is a linearly independent subset of V. This guy. But it may not be a basis for V. I have a linearly independent subset, but it may not be a basis for V. When is it a basis for V? Suppose a basis for a subspace is also a basis for V. What does that say about that subspace and
that
V?
means it generates V.
It generates V, therefore the subspace is equal to V, right?
Yes, sir.
So this is a basis for V if and only if kernel of T is equal to V. And what does that mean for T? Supposing the kernel of a linear map is the full vector space, what does that mean for that linear map?
Every vector like maps to
Every
0.
vector goes to 0. So this is a basis for V if and only if kernel of T is equal to V, which is true if and only if T is the 0 linear map. What do I mean by 0 linear map? I.e., TV equal to 0 of V tilde for every V in V. Is everybody agreeing with me so far? So it can happen that L equal to N But that happens only if the linear map T is just the stupid map that sends every vector in V to the zero vector in V hat. I keep confusing V tilde and V hat. Sorry, I should just use this notation on the right. V, yeah. So is this point clear to everyone? So let me go again. So I have a linear map. So we are okay. Let me rewind. This is what we want to prove. We want to prove this guy. Given a linear map, I want to prove this. So I take the vector space V. I take the subspace, which is the kernel of T. I choose a. Now I am assuming that I'm giving a notation that the dimension of V, it's assumed that V is finite dimensional. So I take that dimension and give it a notation. So this is just a notation for the dimension. I'm just calling the dimension N. It's a natural number because we don't want to deal with the trivial situation. It's even a positive integer. Okay? And the kernel is a subspace of V. So it will have dimension. It could have zero dimension. Supposing the kernel has zero dimension, what does that mean? That means the kernel consists of just the zero vector, in which case the map T is. So let's understand the. So I'm going to take a pause, okay, just to be sure everybody understands. I'm going to make a little detour, okay. Detour. Kernel of T is a subspace of V. This is dimension N. This is dimension L. So we know that L is less than or equal to N. And of course, because L is a dimension, we have this. So the two extreme cases are L equal to N and L equal to 0. So what do these extreme cases mean? So L equal to N means kernel of T is equal to V. And so let me, instead of saying means, I'll say if and only if and only if T V equal to 0 V. T is the zero map. Now, if L equal to 0, this is true if and only if kernel of T consists of only the zero vector. And this is true if and only if T is, now I want you to complete this sentence.
Injective.
It's injective. Yeah. It is 1-1. So this is an exercise that I hope you proved earlier, that if given a linear map, it is 1-1 if and only if the kernel consists of only the zero vector. So we are interested in L anywhere between dimension N and 0. So let us actually, in fact, let us prove, let's continue this detour. Okay, I'm not finished with the detour. Let us prove the rank nullity theorem in these extreme cases. So rank nullity theorem in the extreme cases. So first of all, let us do, supposing L is N. Then what is the image? Let me ask a person at random. Let me ask Advik Jagannathan. Are you there?
Yes, sir.
Yeah. So I'm asking you, supposing L is n, that means then what can you say about the image of T?
It will be the set containing only the zero vector.
Very good. Okay. Does everybody agree with this? Right? Because we have more or less seen this before. If L equal to n, that means the kernel is equal to V. That means T just sends everything to the zero vector. Therefore, the image is the zero vector. So it is the 0 V hat. Is this clear to everyone? Rishabh Gupta, you are just above Adiv Jagannathan.
Yes, sir. Yes, sir.
Yeah, okay. Yeah. How about Abdul Halim? Are you there?
Yes, sir.
Do you agree with this?
Yes, sir.
Okay. So, my question is, can we in this case, let us check. Okay. This is n. What is the dimension of kernel of T? Well, it is n. And image of T consists of only the zero vector. So what is its dimension? There is, the basis consists of there is no linearly independent set, but the dimension is 0. And now if L equal to 0, then if and only if T is injective. So if T is injective, this refers back to the question earlier, right? So let me, who asked this question about, Shakti asked. Yeah. So if T is injective, what does that mean? If going back to, if UN is a basis for V, then TU1, TUN is a basis for the image. So this is a case, if T is injective, then in fact, if I take a basis for V and take the image vectors, that's actually a basis for the image. I will prove this in a minute. Therefore, dimension of V equal to n equals to dimension of image V, image T, and dimension of kernel is 0 because the kernel consists of only the zero vector. So again, the rank nullity theorem is true. So okay, so then everything depends on this claim. Proof. Okay, let me give this proof. Okay, so Shakti, pay attention, because this is a case where your guess is actually true. That if I take a linearly independent set and take the image, I get a linearly independent set in the image. So here is the proof. Okay, so suppose lambda 1, lambda n are scalars such that lambda 1 TU1 plus lambda 2 TU2 lambda n dot TUN is a zero vector in V hat. This by linearity is T of lambda 1 U1 lambda n UN by linearity of T. Now, this implies that lambda 1 U1 lambda n UN belongs to the kernel of T. But if T is injective, since T is assumed to be injective, lambda 1 u1 plus lambda n un is actually the zero vector of V. But u1 un is a basis for V. So lambda 1 equal to 0, lambda 2 equal to 0, lambda n equal to 0. Which proves our claim, which proves that TU1, TUN is linearly independent in image T, but they also generate image T. So dimension of image T is n, as promised. So this is the end of the detour. So in other words, we have proved the rank nullity theorem in the two extreme cases. So again, let me stop here and ask Srimati, is this clear to you?
Yes, sir.
Yeah, very good. So is everybody with me now so far? Sampriti Pillai, are you happy with the discussion so far? Hello? Sampriti, are you there? Apparently not. How about Avinash Rathore?
Yes, sir.
Are you happy with the discussion so far?
Yes, sir.
You don't sound very convinced. You have very low. Yeah.
My mics were not very fixed or whatever.
Your mic is okay. Okay. So can I assume that everybody is on board with this? Yeah. Sagnik Dasgupta. Okay. Very good. Yeah. Swaminathan.
Yes, sir, it's clear.
Yeah, so I am just calling people at random, and people seem to be okay. Okay, so now we have to deal with a general case where kernel of T is neither the full vector space nor just the zero vector. So something in between. So now the general case. So in other words, n is L is strictly bigger than strictly smaller than n and strictly bigger than 0. So L is at least 1, and so this means that n is at least 2, by the way. So to have this non-trivial situation, you need to have at least a two-dimensional vector space to start with. Because if V has dimension either 1, then either T is injective or it's a zero map. So now you have the situation where I have V and I have this linear map from V to, which now I'm drawing it down just to, because I like to, and I have kernel of T. So, and since L is strictly less than n, this is not equal to this. This is a subset, but it's a proper subset. And since also, because kernel of T has dimension at least 1, but it contains the zero vector, but this also is a proper subset. So this is a situation that we have. I have a linear map whose kernel is not 0. On the other hand, it's not the full vector space. So this is the situation we have to deal with. And let me label the dimensions again. This is dimension n, and this is dimension L, and L is in this range. So now we have, what do we do is let V1 to VL be a basis of kernel of T. So that means what? It is a set of vectors which is linearly independent and generates the kernel. So since it's a linearly independent subset set of vectors in the kernel, it is a linearly independent set of vectors in the bigger vector space V. Because if there was a non-trivial relation between these vectors in V, that would hold if I think of these as vectors in the subspace. Okay, so this is a basis. Therefore, V1 to VL is linearly independent subset, is a linearly independent subset of V. Now, it is one of the facts that I have given in the notes, which I have not talked about in class, but it's, if you have read the notes carefully, you would have seen that and you would have proved it for yourself. So this is why reading the notes carefully is important. If I'm given a finite dimensional vector space and any linearly independent subset, I can complete that to a basis. I can add more vectors to it so that I get not just a linearly independent set, but a generating set. Okay. So add vectors, add, how many vectors do I have to add to this? Because because any basis of V has n elements. So if I complete this by adding vectors, then the total set must have n vectors. I already have L vectors, so I must add n minus L vectors. Add n minus L vectors to this subset to get a basis. Okay, so I have to have a notation for them. Now let me choose a notation in the notes. Yeah, there's an obvious notation. I have V1, VL, and the vectors that I add, I call them just VL plus 1 up to Vn. So these guys are belong to kernel of T, and these guys are additional vectors, added vectors to get a basis for V. Is everybody with me so far? Let me see if Sampriti Pillai is back. Sampriti, are you here? Desperately seeking you. Apparently not. Okay. Okay, so now comes a note. So I have this added set of vectors. Let V hat prime. This is a subset of V. V, the span of the added set, which is VL plus 1 to Vn. Remember, given any set of vectors in a vector space, I can take the smallest subspace containing them, which is also the set of all linear combinations of these vectors, which is called the span. So I take the span of these guys. Now, and that's a subspace which I label V hat prime. So consider this VL plus 1 to Vn. This is a subset in V hat prime. It generates V hat prime. And what else? It is linearly independent in V hat prime because it is part of a basis of V. So if there is some relationship, so this is linearly independent. Is this clear to everyone? So the point is, I've taken a bit. So why is this linearly independent? Because if lambda L plus 1, lambda n are scalars, such that lambda L plus 1, we had L plus 1, lambda n, we had n is 0, then 0 times v1 plus 0 times v2 plus 0 times vl plus lambda L plus 1, we had L plus 1, lambda n vn is 0. But v1 to vn are together form a basis of v. Therefore, all the coefficients must be 0. These guys are already 0, and these guys must also be 0. So this not only generate v hat prime, but they are a basis for v hat prime. Conclusion: vl plus 1 to vn is a basis for the subspace v hat prime. Okay, let me see. Yeah. Okay. So is everybody with me so far? Okay. So now let us continue. Can I continue with the proof?
Yes, sir.
Yeah. Debashish, are you there? Debashish Biswal? Yeah, can I continue?
About this proof?
Yeah, can I continue with the proof?
Yeah.
Okay. So now, finally, so we have, so to finish the proof, and I claim, so I'll prove, make a claim, and I'll prove this immediately. A claim, I like to give fancy colors. I claim T V L plus 1 T V N is the basis for image. So in fact, last time I had said something much more abstract. I had said that the image and this v hat prime are isomorphic, and therefore it will have the same dimension. And then, in fact, somebody pointed out that this is what that amounts to, and this is a much more concrete way of thinking about it. So I thank that person, whoever it is. And so let's follow that line of thought. Okay. So first of all, I suppose everybody sees that if you can accept the claim, we are done, right? So first, if you accept the claim, accept the claim,
It should be a comma, right? Not plus followed by T.
Thank you. Thanks a lot. We are home. In other words, we have arrived at our destination. We have finished the proof. Is this clear? Why? Because n is dimension of V is L plus n minus L. This is dimension of kernel of T. And this dimension of image of T by the claim. So if you accept the claim, the proof is finished. Is this clear to everyone? Shakti, are you happy with this?
Yes, sir.
Yeah. So now I have to actually prove the claim. Yeah. Well, this is now easy because we already know that image of T is spanned by TU1, TV1, TV2, TVL, TVL plus 1, TVN. Right? This is generally, we have seen it, in fact, many times, that if you choose a basis for V and take all the vectors that you get on the right by applying T to them, that spans the image. But this is 0 because V1 to V2, VL, they are all in the kernel. So all these are the 0 vectors. So if you have a set of vectors that generates a subspace, and among that set, the 0 vector, first of all, as a set, these are, so if this is there's a small point in a set, you don't list the same element many times. So all this, what this means is the 0 vector once in the set, but I can drop the 0 vector because the set of the subspace generated does not change if I drop the 0 vector from a list of vectors. So this means, this implies image
Just because the span remains the same, right?
generated by TVL plus 1 TVN. So that is the, see, the claim has 2 parts, that this set of vectors is a basis for the image. So I have shown that this set of vectors spans the image. But now I have to show they are linearly independent. So before I do that, is this clear? That if I have taken a basis for the kernel, added n minus L vectors to get a basis for V. And now the claim is that if I take the images of these n minus L vectors in V hat, they generate the image of T. So that is the first step to prove the claim in red. Now we will come to the second step, but I want to be sure that everybody has followed me so far. Bija and Ray. Is it okay?
Yes, sir. Yes, sir.
Yeah, Aditi, how about you?
Yes, sir.
Okay, great. So now I think you can see how the rest of the argument will go, because we have seen versions of this before. We need to now show what is left to show. What is the one step that's
Linear
left to show?
independence.
We have to show linear. Who is this?
Nilabjo.
Okay, we have to show that this is a linearly independent set. Show that TVL plus 1 TVN is a linearly independent set in V hat. Okay, so how do you, so let's do this. Suppose lambda L plus 1, lambda n are scalars such that lambda L plus 1 T V L plus 1 plus lambda n dot T V n is 0 V hat by linearity of T. This is T of lambda L plus 1 V L plus 1 lambda n dot V n is 0 V hat. This implies lambda L plus 1 V hat L plus 1 plus lambda n V n belongs to the kernel of T. But now look, we have kernel of T. So now go back to V. So V1, VL, VL plus 1, Vn. This is the basis for V. V1 to VL is the basis for kernel of T. So if lambda L plus 1 VL plus 1 plus lambda n Vn belongs to the kernel of T, there exists mu1 to mu L such that lambda L plus 1 V hat L plus 1 plus lambda n Vn is equal to mu1 V1 plus mu L VL. This implies mu1 V1 plus mu L VL plus minus lambda L plus 1 VL plus 1 minus lambda n Vn is 0. But this is a basis. V1 to Vn is a basis. This implies mu1 to mu L is 0 and minus lambda L plus 1 to minus lambda n is 0. So all of them are 0. This implies lambda L plus 1 is 0, lambda n equal to 0, which proves the linearly independence of TV1 to TVN.
Sir, could you just scroll down to the last page?
Yeah. I'll scroll down here and I will take a little break and give you time. We'll come back and discuss this briefly before I go on. Okay. So do I need to do anything? I don't need to do anything. Maybe I need to mute myself.
So your screen is not being shared.
Resume the talk. Yeah. So now the new topic is matrices. So everything that you do in linear algebra has a counterpart in the world of matrices, but not everything that you do in the world of matrices has a counterpart in linear algebra. So matrices are important in two ways. First of all, they are a concrete way of dealing with linear algebra. So if, for example, if you want to do any kind of programming, then you have to do programming in terms of matrices. And secondly, they are not, there are questions that you can ask in terms of matrices, which go beyond questions in linear algebra, and they are important. Okay, so you should have a lot of respect for matrices. I'm saying this because I grew up learning linear algebra abstractly, and I did not have sufficient respect for matrices till later. In particular, and this is something that every mathematician should know, at the heart of Google is some really, really sophisticated manipulation with matrices. When you put in the search field for Google, you type whatever you're searching for, and within a millisecond, Google gives you a list of results, and usually the first 2 or 3 are the most important. Behind this is really, really very, very clever things done with enormous matrices. The size of the matrices involved are now possibly, these are trillion matrices of huge sizes, which are involved in the Google algorithm. So it's absolutely fascinating stuff and very, very important. Very good. So anytime that anybody uses artificial intelligence, machine learning, matrices are the heart of it. And also in pure math. Very good. So after that advertisement, so let's start with the basics. So today I'm just going to get you used to notation and a little bit. So this is, but then I think for much of the rest of the course, we will deal extensively with matrices. Okay, basics. So what is a M cross N real matrix? So as usual, as we have done so far, we have specialized to real numbers, but whatever I say will hold with much greater generality, certainly when you consider any field. Okay. So what is a n by n real matrix? So here m and n are integers, and m is greater than or equal to 1, n is greater than or equal to 1. So fix 2 integers, and then you can consider matrices of size m cross n. Okay. So what is this? This is abstractly, this is A m cross n real numbers ai comma j, where I runs from 1 m, and j, the second index runs from 1 to n. Now, because of laziness, sometimes you will write this as aij. Okay. But the point is, now this is ambiguous. If m is bigger than 9 or n is bigger than 9, right? Because supposing, so I don't know, so supposing I write a 10 9. Okay. Do I mean a 10 9 or a, so where to put the comma becomes important. So this is ambiguous, but out of laziness, you omit the comma, especially if you are dealing with sort of algebra matrices. Okay, so I'm not looking at a specific element. So it is best to visualize a matrix as an array of numbers, and you call the array A, and so A11, A12, A1 n, M1, AMN. So Aij will appear at the intersection of, so this is the ith row, row number I, and column number J. So if M is the matrix, I will write a matrix 5, 4, 3, -1, -9, 2. So this is a 2 by 3 matrix, and it's Mij, sorry, is -9. So this is the entry that occurs at the intersection of the second row and the second column. So there is no, so we need a notation because we will be fixing M and N, and in fact, we will consider all matrices of a fixed size. Okay, we will find it useful and in fact important. Consider all matrices of size M cross N. So in fact, that in notation, there are several notations. There is no standard notation. I will often use this notation, curly M cross N R, or if I'm dealing with complex matrices, with complex entries, I will write this. So by the way, these are called entries. So Aij is the ij entry of A. So by the way, so this is also Aij. I mean, so you notice that. So the point is that in this example, I start. So if you start with, see, this is a matter of more of notation and philosophy than anything else. Sometimes I start with the array of the entries being given, and then I have to put the entries together into a matrix, and I call that capital. So the entries begin with the lowercase notation A, small aij, and then I put it together into a matrix which I call capital A. And sometimes I have start with the array, which has a name capital M, and then I have to refer to a particular entry in the matrix, and then I call it capital M22. So so this could be called M22, And so, see, so whether I call this capital M22 or smaller M22 is a matter of where I start. If I start by giving the smaller Mij, then I will stick to that notation. If I start by giving the capital M entry, the array, then I will do. So remember that. So in other words, we will use both these notations. So it's a matter of what you are starting with. Very good. Okay. So this is the so this is a set. Okay. For example, M1 1 cross 1 R. What is that? It is the set of all 1 by 1 matrices. So it has only one row and one column and one real number there. So the set consists of all real numbers, except that when I think of it as 1 by 1 matrices, I must take the real number and put a square bracket on around it. Okay, so far we've mostly talked notation, but now the point is we have actually this set of matrices has a lot of structure. Okay, M cross N R fix M N has vector space structure. Defined as follows. So if I take two matrices A and A prime, so this is size M, size N, M cross N. So both of them have M rows and N columns. So A11, A1N, AM1. So take two matrices. So this is an element of this set. This is an element of the same set. So when I say it has a vector space structure, I should be able to add these two guys and define something. So one second. So this is the matrix A plus, so one second. Let me be clear what I'm doing. I'm taking, let me put this division, this line between them. Yeah, so I'm taking two elements of the set. Here's, sorry about that. I'm taking two elements of this set of M cross N matrices. So take two M cross N matrices. The first matrix is called A. The second matrix is called A prime. A consists of an m cross n array of real numbers whose entries are labeled A11, A1n, A prime. I think this is what somebody was worried about, maybe. And the second matrix says that the entries are called A prime, 1, 1, etc. And then I must get what is the sum of these two guys, because I'm making this a vector space. So the sum is this matrix. So this is how the sum of vectors of matrices is defined. Take this matrix, and you get this matrix. You take the corresponding numbers and just add them up. Similarly, scalar multiplication.
Just a second. So, why did you write m cross n in brackets A? And under belongs to.
Sorry, A plus A prime belongs to what?
No, sir. Each individual matrix A belongs to the set of m cross n in brackets A. Not R. Sorry. So thank you. Thanks very much. Yeah. So this will also belongs to scalar multiplication. Well, if I take a matrix A, A11, AM1, AM1, AMN, and take a scalar lambda times this matrix, you just each component, each entry gets multiplied by lambda. It's the most obvious thing you can do. But it does make this into a vector space. Okay.
So the last
so
entry should be A1n, right? I mean, horizontally, when we move from A11 to.
Thank you. A1, yeah. Thank you. Very good. I will stop now. Yeah. Just 1 second. I'm going to now stop the recording because we just wanted to, just briefly see this. We will do this more